I mean, it is a big deal, and part of the challenge is demonstrating to people that this is a better way to do things. I mean, you know, a lot of this really is inertia. I mean, you could come up with a better technical solution. I mean, and to the people in this room, the fact that it's better may be completely obvious, but, you know, some guy, you know, doing his research at a university for the past 30 years, and he's been doing things the same way, it's a little hard to reach some of those folks. So it's going to be a little bit, I think, of an evolution, and I think you have to really come up with, and this is something that we're trying to think about, how do you come up with solid examples to show people this will make your life easier, this will amplify the impact of your science. You know, if you can, this will open up a whole new world of possibilities for your research. And I think the conveyance of that message and repeating it is really what's going to, how it's going to have to happen. It's going to be sort of a brute force. It's not just going to be if you build it, they will come, right? Which is what we found.
The HPC community is also grappling with that, where we are wanting in situ analytics and not generate a whole bunch of simulation output and then reload it, which will take 20 minutes sometimes if it's multiple hundreds of terabytes. It's somewhat similar.
So there's an interesting, God, this is loud, divergence. So there was a period of time, it was about 5 years ago, I think, where commercial enterprises, as well as government, said, you know, storage is cheap. File-based storage is cheap. We don't have to worry about that anymore, however much you want. But that was because the level of effort and resources for a given amount of storage was easy to define. And there is not a comparable confidence in terms of computing. So I don't think people anymore, they used to anymore, are opposed to doing their computing close to the data, but those that are providing the unlimited data storage, one, do not provide unlimited computing capacity, and two, don't really know how to judge what's that level of resource. So, for example, Earth Engine will say, store whatever you want. And they'll say, and you can compute almost anything you want, but we'll tell you when it's too much, because we don't really know what that's going to be. So there's definitely a challenge of being able to specify, measure, and thereby commoditize the computing, in which case you can rely on the in-situ computing that people are providing.
One more point, just to follow up on that, it's an excellent point, and I think one of the things is NASA is actually in the process of trying to incentivize this kind of thing, because you're right, some of the competitive programs have been, you know, ways for these guys to build up the hardware in their labs, you know, over the years, and NASA's trying to move away from that, trying to say, okay, you know, you can't dedicate 25% of your award to buying racks of hardware. I'll give you credits to do this work in the cloud. We'll make all the data available you need, and this is where you're going to do it. So there's a bit of a carrot and a stick kind of thing. I think.
Thank you. So.
I have the microphone already.
Let me chime in for a moment. So actually, this was an excellent. A lot of microphones switch off. Let me just say briefly. I believe there is really a link to the database talk before, because I believe one big obstacle for doing that data sharing is just what is the right kind of interface. We know that our classical web services have hit a wall with just a simple function, maybe parameterized, that gives us something that is too inflexible. On the other hand, just shipping code in the sense of sending Python code or so. Number one, it cannot be optimized. Number two, it's dangerous. Number three, I don't want to write Python, I want to have my query answered. So in the middle, we have the declarative query languages, which are set out to do that. And our task, actually, I believe, is to find out what that would look like for geodata. We have that role model. Once again, for business data, SQL works well. By the way, we also have such things in OGC already. Just one example, the web coverage processing service is a declarative query language on data cubes. So such a thing is available. And I believe, personally believe, that query languages are the way forward indeed. Whether there is a database behind or not doesn't matter. And it's just a nice client-server interface. Okay, my 2 cents. There was
Get Ted, and then we probably should wrap up and move on.
We've got this one, some really exciting stuff. It's smaller and more powerful than yours.
Pop. Let's get out for a minute.
It has a laser too.
That was your question? Okay, thanks, Ted.
Yeah, I think that Peter's right, that what we're thinking about at HDF is really sort of a stable API, and SQL is certainly a good model for that. And tools that can move across various different backend storage strategies. So I think the reason that we're still in the download mentality is because most of the tools only work on local file systems. We have a good example of this in the NetCDF history, where the NetCDF library incorporated OpenDAP, 15 years ago, and all of a sudden, if you had a file name that started with HTTP, then it was going over the network to get the data. So it was completely transparent to the user. And I think the problem that we're thinking, the way that we need to think about this download thing is how can we enable that kind of access without changing the tools? So basically, you get a new version of whatever, and all of a sudden it does the access. It does remote access rather than downloaded access, and I think that's the real problem that we're facing is just not the download mentality. It's these are the tools I've been using forever.
We need new tools.
Thank you. I'm sorry, Ted. I need to confiscate this. Okay. So let us proceed. Thanks again, Glenn, for this talk. And I see how we are warming up. And now the last talk is given by Rob. I need to have a quick look on my sheet, which has gone great, because your name was
On the screen.
Your name was announced wrongly. So Azavia is the correct one.
Yeah. I have to apologize.
Okay.
It's
Can
okay.
you tell us how to pronounce it?
We put the wrong company name on the website for a while.
Yeah.
We're very
And it's a company
embarrassed
we've
about
had
that.
weird legal battles with naming
Is that
stuff.
right?
Yeah, so
Yeah.
it's not a good situation.
Okay, so Rob is going to give a talk
Sure.
here, and he is coming from LocationTech and Apache Foundation. So we have a nice extra voice here, and now you can pick which microphone to take. Yeah, this one.
Testing. All right. Hey everyone. My name's Rob Emanuel. I'm from a company called Azavia. It's a geospatial software development company in Philadelphia. So I do software development. I work on a project called GeoCharles, which I'll be talking about in a second. So just to go over what we'll be covering, just want to talk about some LocationTech projects that geospatially enable Apache big data framework. So we heard a little bit about Apache projects, and somebody mentioned how they're not like something like Hadoop or HDFS isn't geospatially sensitive. So we'll be talking a bit about that, and then kind of get into some more technical detail about how 4 of these projects approach indexing and focusing on using space filling curves to kind of solve the problem of how do we do fast access on a distributed file system for spatial and spatiotemporal queries. So when we talk about storing and processing geospatial data at scale, I like to remember that we're talking about processing data at scale, right? And there's a lot of work here that's been done, and a lot of projects and frameworks that support big data, and a lot of people working on those projects. I think geospatial is sort of a smaller subset of a larger whole, and that larger whole has a lot of really smart people pushing forward development on and not thinking about geospatial stuff. So it's like our job to figure out how to put the geospatial angle on it. The Apache Foundation has 3 projects that I'll mention: Hadoop, Accumulo, and Spark. Hadoop, I think we all kind of know what these projects are, except for Accumulo. Accumulo is a NoSQL, a big table sort of clone on top of HDFS. So it's viewed as a database, and I'll talk a little bit more about that later. And then so they're not geospatially sensitive, let's call it, or geospatially enabled. So the 4 projects that I want to talk about today actually geospatially enable these Apache projects. And they're all housed at LocationTech. So what is LocationTech? Well, it's a working group inside of the Eclipse Foundation. Eclipse Foundation is, a lot of people know Eclipse as the IDE, but it's a software foundation, kind of similar to Apache Foundation or OSGeo, that focuses on open source projects with a commercial friendly license. It just means stuff like Apache 2.0, the EPL. And they have like sort of a team of lawyers that help you, make sure that you're being a good open source citizen and have clean licensing. And they have a number of working groups under it, LocationTech being the one that focuses on geospatial projects. All right, so we have a number of members, and it's a governing organization, and there's various participating members, OGCs in there, so that's great. So there's some. It's a place, for me, it's a place where projects kind of call home and collaborate on geospatial technologies, and also organizations kind of put their minds together and think about how these technologies can solve sort of all of the problems that I've been hearing today. Like, these are all really great problems that we're all kind of thinking about and trying to solve. So how do we have conversations around that? Yeah, and as a developer, to me, it's like this list of projects, right? These are the other projects with developers that I collaborate with, and they're all, most of them are based on JVM stuff, so Java, Scala technologies. There's a C++ library in there as well. But I want to talk about these four today. That's GeoGenie, GeoTrellis, GeoMesa, and GeoWave. The names are not very original. Geo is the next project. And specifically, I want to talk about, because I don't have too much time, I can talk a lot, but I want to talk about how the storage of geospatial data in a distributed environment necessitates the use of a spatial index. So I'm going to focus on that, how the projects actually kind of implement that. So GeoGenie is formerly known as Spatial Hadoop, but legal reasons Apache was not too cool with having Hadoop in the name. But really it's something that geospatially enables Hadoop. So if you're working purely in Hadoop, in a Hadoop environment, it might be good to check out. And so their technique is different than the other techniques, which I'll talk about in a second. But HDFS is a distributed file system. So there's these shards of data across a cluster, right? And so if we take a coarse gridding of that cluster, either spatially or spatiotemporally, and we take a coarse grid, we can kind of say, okay, this query only hits these 3 file sets, right? And then so that's like sort of the coarse gridding that it does, and then it actually creates a static spatial index for all of the simple features in each of the files of that coarse grid, right? So a query might hit 4 of the coarse grids, and then it'll distribute those out and then read in a spatial index that was built on ingest and do a spatial query at that point. And then those 4 files are actually just, made out of blocks that are distributed across the file system too. So it's parallelized in a couple different ways. And so it's different than what I'm about to talk about because it's sort of like this static index that's built up at ingest time. So for instance, like an R tree is one of the indexes that they support. It kind of looks like this, where it goes down into various levels of resolution, and it's like a B tree but in 2 dimensions. So that's how GeoGenie focuses on indexing. It actually stores a static index. These 3 projects take a different approach that I'm going to talk more about today, and that's space filling curves. So space filling curves, for those who don't know, it's basically a continuous curve that completely fills up the unit square. So if I have a 2-dimensional square, if I draw a curve that's continuous throughout the whole thing and I actually hit all of the points, that's a space filling curve. And as you notice, it doesn't really hit all of the points, but there's actually like iterative approaches that build up. So this is a Hilbert curve And if I take this recursive iterative approach, I can eventually, if I take the limit of this, it'll actually hit every point in space. And we don't actually use the complete indexing of the whole entire, every single point on the real, real squared. We take some version of this and call it a specific resolution, right? So there's, if we cut up our 2D space like this sort of first degree of resolution is the 4 quadrants, and the second degree of resolution would be the red boxes, third degree would be the green boxes. And a useful property of many, if not all of the space filling curves, at least that we use, is that the bits that they start with actually always are true. So if a point is in the top quadrant, it doesn't matter what spatial resolution you're looking for of that cell, it'll always start with a 1-1, which is kind of nice. So the idea behind space filling curves can be kind of like drawn out like this, right?